All right, so are we live? I think so. Let's see. Howdy. Howdy. Welcome. Hello, hello. So the deal is, oh man, I'm really tired. Oh. Whew. Yeah, solve another problem. This plan. I think I'm gonna solve a problem, and then I'm gonna hit the gym, do some back exercises. I was, what do you call that? I was having a hard time sleeping because I was so excited about the future. But what I was gonna do during the day, I couldn't sleep. It's so weird. But one of the things that came up was in my mind was exercising. You know, like when I was a youth, 17, 16, 18, 16, 17, 18, around that age, I used to exercise like twice a day. I mean, I used to exercise like crazy. And the idea was I wanted to be a football player, I wanted to be a professional football player, and I wanted to be a lot stronger. I went from like 100 and what was I? I was like 190 something pounds. I dropped down to like 165 pounds, 170 pounds, and then I put on another like 20 pounds of muscle, something like that, something crazy. I don't remember exactly what, but I was back up to like 190, and I was mean, man. I was so strong. Um, but I got a lot bigger since then, and a few years ago I was like 265. I would like to get back to that weight, around 265, 270, and like mostly muscle, be like really, really big, really strong. But that's like more weightlifting than it is running. You don't really do too much running, just lift weights. So I'll do that later today. But yeah, I think if I just exercise like every day, you know, I do one 2K on the erg, it's called. It's a rowing machine. Do like 2,000 kilometers on the rowing machine. That's like pretty good cardio. Do that every day, and then each day just rotate, do like back exercises, you know, backs and biceps, chest and triceps, and then legs, and just kind of do all three of those. I think after a while I'll just be very very toned and muscled and all that, and just go slow, you know, just go take it a day at a time. So here's the question today, or another question. Range sum query 2D immutable. Given a 2D matrix, find the sum of the elements inside the rectangle defined by its upper left corner and lower right corner. Find the sum of the elements inside the rectangle defined by its upper left corner and lower right corner. Interesting. The above rectangle with the red border is defined by, okay, contains sum 8. Really? Is that it? Just sum the region? Immutable? You may assume that the matrix does not change. There are many calls to some oh, okay, interesting. I may assume that. Alright. I was going to say, I was like, there's a catch here. I know what the catch is. I'll explain in a minute. There are many calls to this region function. You may assume that. Alright. So what you do is it's a pre-processing step. So when you build the matrix in the first place, basically what you're going to do is you're going to take the sum of, you're going to build a second matrix, which is more or less the same, you know, similar to the same size. You're going to build a pre-processing step that builds a second matrix, and what that matrix is going to be is actually the sum from left to right of each row, and then also the sum. Actually, you could build two matrices, I guess. Sums from left to right, and the sums from top to bottom. And the reason you want to do that is when they give you the sum of a rectangle, you want the, well, actually, you can do it the other way around. You can do, I'm actually not sure now. You can easily, so you can do a pre-processing step to easily get the sum over a particular row. Let's start with that. We'll do it that way. So if you were to do that, what you would do is you'd say, you know, if you have like the sum up to here, and the sum up to here, and then you just take this part, subtract this part, and then add the value back that you removed here. Or rather just subtract, you have sum up to here, sum up to here. If you wanted this sum, you would just take this one minus that one, right? Something like that. That is how you would very easily get, very quickly, if you're doing lots and lots of calls, how you'd very quickly get the, what's that called? The sum over that range. What's tricky about this, though, is you actually want the sum over a whole rectangle, which technically you could just add each of these, the row, like however long each of the rows, however long the, however many rows you have, you can calculate them each. And basically, the pre-processing step after that, it would be constant time to calculate all of those. The problem with that, though, is you don't just want you may want to be able to do that even faster. Like you might want to be able to take this sum and do it in constant time. I think you can. Basically, if you took that accumulated function and then you added them down each column, right? Added each row sum and each column sum, and you created another matrix, another vector. I guess what that would look like is it would be the sum. Each of these numbers would be the sum over the whole rectangle from the top left to that corner, that bottom right corner, right? Like it would be like this, like here, right. So that's kind of interesting, because then what you can do is subtract the numbers you need to subtract are, it's this rectangle above here, so this number you would subtract, and then also you'd want to subtract this rectangle and then add back this one. That's pretty interesting. But yeah, you could still do that. So it's just one matrix. First you get all the sums left to right. Then you get all the sums of those sums top to bottom. And then when you want a particular rectangle, you're going to add this rectangle, this rectangle. Really, it's this rectangle, and then subtract this one, and then add back this one. Oh, that's super interesting. Yeah, that's kind of cool. That has to do with the overlap, right? You would add this whole thing, and then add this again, add this, or subtract this, and then add this back. Wow, that's very interesting. The thing that's kind of tricky about it is, what if these don't exist? Like, what if it goes all the way from this? It's sort of like edge cases, right? If those elements don't exist, which they could, right? Because this rectangle could be like, if it's on if it's on both edges, then you just return that value directly. If it's in other words, if this point is all the way up here, if it's on this edge, then you don't need to do the full, all four additions, subtractions. You just subtract this one rectangle. If it's on this edge here, then you just subtract this one. So yeah, so there's like a little bit of edge case going on, but overall, it's really interesting. This is a cool question. I like this. It's fun. Give me 1 second, but yeah, pretty simple solution though, I believe. One pre-processing step, visit every element once, and then after that, all the queries are basically constant time after that. Hold on 1 second here. Yeah, just have to finagle a little bit with the bounds. Yeah, it should be okay. All right, let's try it. Let's give this a shot. See how this goes. See how this goes. We're actually going to use a constant matrix, private. Oops. Preprocessed or I don't know, PM, preprocessed matrix, something like that. And we're going to say for int I equals 0. So we're going to do actually row columns. Do row and rows equals matrix dot size. Yeah, we can try this. If I'm not really sure what to say here. So we're assuming it's a 2D matrix. There's gotta be, yeah, they both have to be non-zero, right? Otherwise the matrix is just empty. The matrix, if there's no rows, or if there are rows, but each row, each column, there's, you know, there's no columns. If it's just empty, then we just return, I guess we'll just say bool empty. And then, okay. So otherwise we can say number of rows, matrix size, number of columns equals matrix of 0 dot size, number of rows, number of columns. Okay. So first we're going to do for each row we're going to accumulate rows from left to right. So for each row we have a sum int accumulate 0, accumulate plus equals matrix of RC, and we're going to say, you don't even need to accumulate, you can do it this way. You can just say matrix or PM is going to be equal to PM of RC is equal to, so first we say PM of R0 equals matrix of R0. Start with that, and then we say matrix of RC is going to be, it's going to be PM of the same row, decrement the column, and add matrix of RC. Yeah, there we go. Do it this way. Accumulate rows from left to right. Accumulate columns from top to bottom. Like so. So now we do columns, rows. So for each column, we want to say this PM, so we don't actually need to modify that value because now PM will be initialized properly. And we're going to say PM of column or row column. I'm just thinking. So the first column is set properly for the yeah, same thing. Yes. So the first column is set first row is set properly. Oh no, the first column, row equals 0. The first column is set properly on the first pass. On the second pass, the first row is set properly. So we basically just skip the first row altogether. And we say row minus 1 of that column plus I realize this looks kind of funky, but now, so what we're going to do is the first row is fine, but each column now we're modifying. So we're looping, we do one column, it's going to be every row, or every row, we're going to update that column spot and that row spot with the previous row's column, you know, adding this value to what the previous row was, right? I realize it looks a little confusing also, but that should be correct. So accumulate rows from left to right, accumulate columns from top to bottom, and then now PM represents the sum of a rectangle from position 0, 0 to row column. There we go. Boom. That pre-processing step, that works really nicely. Now our sum, we have right rows, columns, and let's do R1, C1, and R2, C2. Super interesting. So now we say, so if R1 is not equal to, is greater than 0, and C1 is greater than 0, it really matters on where R1 and C1 are. So we'll say we'll start with int ret. It's going to be PM of right R2 C2. Assuming these are R1 is less than R2 and C1 is less than C2, right? If these are inverted, then this is going to get really confusing. They assume that these are true. Yeah, I was going to say this is, yeah, you can give faulty input. Just write that. Assume you would normally put some kind of sanity check. To sort of fix that. Something, either throw an exception or actually reverse the two values, something along those lines, or just give you literally a negative, the negation of that major rectangle. So, all right, so if R1 is greater than 0 and C1 is greater than 0, then you're going to say ret equals ret. You're going to say minus equals or yeah, we'll do ret equals ret minus. You're going to add 2 points, which is going to be the row. It's this part. It's the row minus 1, row 1, which is here, minus 1, this row, but the same column 2. So row 1, but column 2. And then also going to subtract, I think, the other side, which is row 2, but column 1. And it's actually column 1 minus 1 and row 1 minus 1. That's why these need to be non-zero. And then finally, you're going to add both row 1 minus 1, row 2, column 2 of column 1 minus 1. It looks a little crazy, but this is Also not doing sanity checks on assuming and greater than 0, R2, 0. Or just in bounds. Yeah, also assuming these are in bounds on the on the matrix. Yeah. Okay. So if R1 is greater than 0, so the row is greater than 0, but the column is not for this point. So the column is the first column. Then you're going to return ret minus just this guy, this 1. This is basically this one. It's got to be this one, right? Yeah. So it's a little confusing. Quite frankly, it's a little confusing. But this is how it is. So if you say R1, so if C1 is greater than 0 and R1 is equal to 0, then you're going to do the other one, which is it's R2 C1 minus 1. And you don't add back this piece. And now otherwise return ret. If now if they're both C1 and R1 are 0, right, then you just return ret as it is. Something like this. Undefined behavior, nice. Num matrix. What is the null pointer of type undefined behavior? What? We just want to say if empty returns 0. What's going on? Where is this happening? Okay. Huh. Did we get that far? No. What is going on? Hello? Why is this happening? We get the first test, and then after that, we have failure. Oh, I know why. I see. That's why. Got it. Understood. Gotcha. I see the problem. That's my mistake. Did not initialize this properly. Yeah, so the number of rows is number of rows, and then we're going to initialize the number of columns to the number of columns 0. That's probably why. Test 1, 2. Okay, that's a little bit better. Okay. What's wrong now? -4, -3, -2. Nice. Not what I was expecting. 2, 1, 4, 3. 2, 1, 4, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 4. Uh, 2, 1 to 4, 3. She had 8. Well, we got -4. How did that happen? 2, 1, 4, 3. What do we get with these? What do each of these values give me? What do we get in each of these cases? 12, 10, 4, 12, 10, 14, 1, 2, 3, 4, 12, 10, 14, and 8. 12? That's what we expect. This is, what is this? 4, 8, plus 11, plus 5 is 16. So that's 24, plus another 3, 4, 28, plus another 5, 6, 34, plus another 4. It should be like 48. Why is this 12? Oh, that's why. This is, I'm sorry. This is supposed to be PM. That's why these are too small. There we go. Okay. I was gonna say, this should also be like a really quick question, quick answer. I mean, figuring it out is pretty quick, but for whatever reason, coding it for me took me a while. Like it really, I feel like it shouldn't have taken me so long, but I don't know. This part kind of tripped me up. Getting this right. It's pretty simple, you know. It's just the rows and columns that are non-zero are the ones that you have to subtract, and obviously the one you subtracted, you know, each of these cases are such. The ones you subtract are the ones that have the non-zero part, right? That's the part you decrement. It's just one of these, one or the other. Yeah, I mean, okay, you know. Should we just go for it? I kind of want to just go for it. See what happens. Hey, got there. Yeah, the reason being, I don't want to mess around with, I don't really want to mess around with, like, a couple things. I mean, if this was wrong, then I'd be kind of stuck. Also, I wouldn't expect this to be wrong, and there's a lot, like, the different possible test cases that I could come up with would be, it would take a while. That's kind of really why I just wanted to go for it, because I don't want to mess around with all the different test cases. There's like quite a few for this. So anyway, all right, that took a while, didn't it? It also took 30 minutes. Man, I'm trying to solve these in like a few minutes, and here it is. It takes me 30 minutes. That's like not a 30-minute question at all. That's like pretty much a few minutes. But I would say with this problem, there's a lot of ways that you could have bad inputs, and that could really cause a lot of problems. Like that could take a lot of time, just kind of handling all the different edge cases with bad inputs. Assuming perfect inputs, this should be pretty quick. Yeah, I got tripped up here. I forgot to initialize this matrix properly. And then I also didn't, technically you could just modify this matrix directly, you know. I probably would get faster runtime and better memory usage if I modified this matrix directly. Although it says it's immutable, right? So maybe it's better to not touch it. Yeah, I mean, just thinking what else I want to say here. I mean, this makes it pretty easy you can memorize that basically, and just, you know, for the parts that are greater than 0, those are the parts you subtract. You flip row 1, column 2, and column 2, row 2, column 1, and then those are the two pieces, right? Just combine row 1 with column 2 and column 2 with row 1, and row 1 with column 2 and row 2 with column 1. And then obviously the first point is the one you subtract. So that's the one that has the minus 1 on it. And then the last part is both row 1, column 1, or subtract 1. And then you only subtract one piece, and the piece you subtract is exactly one of these two, and it's exactly the one we do the bound check for whether or not it's 0 or 1. I mean, here you literally could just remove this and make it 0. Oh no, I'm sorry. No, I take that back. No, no, never mind. Take that back. Yeah. So 4 different cases really matters. The whole point of this else if is the first rectangle. So we have a whole rectangle sum, and then there's a sort of a second point above and to the left of that other point that kind of denotes which portions of rectangles we want to remove. We don't want to include in our total sum. Yeah, that's kind of the deal. Yes. So what are we doing here? I was just thinking, like, what else I want to say? Like, how to get this faster next time. That's pretty quick. I mean, that's not too bad. 30 minutes. Yeah, I mean, did get tripped up here. Got a little tripped up here. I forgot to use the right numbers. This took me a little while too to kind of sort that through, the logic there. There's sort of 4 different rectangles to consider. Because these rectangles don't even exist in some cases. That's kind of why it took me a little while to think about it. 4 different cases, because you want to make sure the rectangles even exist, and if they do exist, then you're going to subtract them. So I think that's why I kind of stumbled on this a little bit. Like, this rectangle always exists. However, the other rectangles, you have to kind of figure out what you want to do. What if you did all zeros here? What did you get? If they're all zeros, you would just get yeah, it's just if it's all zeros, then actually you just you would just get this one value at the top, this one. be like a 3. Yeah, right. I think so. Because you would fail this, fail this, fail this, and just return 3. Yeah. Very interesting. Very interesting. All right, let's move on. So yeah, thank you for watching. I appreciate it. I will talk to y'all soon. Take care. Have a good rest of your day. I think I think plan is exercise, and then come back and keep doing more problems. So yeah, take care.